Huawei started to cooperate with car manufacturers, and people wanted to see how Huawei.
What if you could pull into an electric vehicle charging station, step away for a quick coffee break, and return to find your battery fully replenished? This isn't wishful thinking or the distant future. It's exactly what Huawei's latest patent promises. If accurate, this would represent a major shift in battery performance compared to what's currently available. The patent describes a solid-state battery that could significantly reduce charging times while extending how far an EV can travel on a single charge. Huawei is best known for its work in telecom and consumer electronics, but this patent shows they're now making serious moves in energy storage. Of course, a patent doesn't guarantee a working product. Translating lab concepts into real-world battery packs is a complex process. In this video, we'll go through what's in the patent, the chemistry behind it, and what the result might mean for EVs if the technology actually reaches production. Imagine driving farther than most gas cars allow and recharging in less time than it takes to order coffee. But what exactly is inside Huawei's mysterious new battery patent? Patent reveal and headlines. Earlier this year, Huawei filed a patent in China for a new type of solid-state battery. The document describes a cell that uses a nitrogen-doped sulfide electrolyte. According to the filing, this design could reach energy densities between 400 and 500 watt-hours per kilogram. That's roughly double the energy density of most lithium-ion batteries on the market today. Under China's CLTC testing cycle, the battery would offer a range of up to 3,000 kilometers. Even under the more conservative EPA standard, the estimate still exceeds 2,000 kilometers. The patent also claims the battery can fully recharge in 5 minutes. For comparison, the fastest EV chargers today, rated at 350 kilowatts, usually take at least 15 to 20 minutes to charge a battery to 80%. Going from 0 to 100% in 5 minutes would require a completely different approach to battery design, thermal management, and charging infrastructure. It's important to note that patents represent technical concepts, not finished products. The numbers can be based on ideal lab conditions and may not account for the challenges of real-world manufacturing. Still, the publication of this patent attracted attention. It was widely discussed in online forums and mentioned in investor circles. Stock prices for several EV companies moved noticeably following the news. One of the key innovations mentioned is the nitrogen doping process. By adding nitrogen to the sulfide electrolyte, the design may improve ionic conductivity and reduce dendrite formation, which is a common failure point in solid-state cells. The patent also shows a nano-coated cathode, where each particle is covered in a thin oxide layer. This could help reduce unwanted chemical reactions between the cathode and the solid electrolyte, potentially improving battery life and safety. Huawei is not the first to explore these methods. Companies like Toyota and QuantumScape have been working on similar concepts for years, but none have brought a solid-state EV battery to full commercial production. Huawei's entry into the space adds more attention to the ongoing effort to improve battery technology, especially in terms of safety, speed, and energy density. Solid-state chemistry. Huawei's patent is based on replacing the liquid electrolyte used in most lithium-ion batteries with a solid alternative. Solid-state batteries are designed to move lithium ions through a solid material instead of a liquid. The goal is to improve safety, increase energy density, and allow for faster charging. Several types of solid electrolytes have been researched over the past decade. Ceramic electrolytes are durable and handle high voltages well, but are prone to cracking under stress. Oxide-based materials offer a balance between performance and stability, but require carefully controlled production environments. Sulfide electrolytes, which Huawei's patent focuses on, have good conductivity at room temperature and can be formed into thin, flexible sheets. However, they are extremely sensitive to moisture, which makes manufacturing more expensive and technically demanding. In Huawei's design, nitrogen atoms are added to the sulfide structure. This adjustment is meant to improve the flow of ions through the material and reduce the growth of lithium dendrites. Dendrites are tiny, needle-like structures that can grow during fast charging and eventually cause short circuits. By strengthening the grain boundaries inside the electrolyte, the nitrogen doping may help prevent those failures, especially during high-speed charging. The patent also describes a special coating on the cathode particles. Each one is wrapped in a thin layer of oxide, which helps reduce chemical reactions between the high-voltage cathode and the solid electrolyte. These side reactions can lower performance and shorten the life of the battery. A protective coating helps to keep the chemistry stable during repeated charging and discharging cycles. While the design shows promise, it's worth remembering that many companies have published similar ideas over the years. Toyota and QuantumScape, for example, have spent significant time and money developing solid-state cells, but they've faced major challenges in bringing them to mass production. Making these materials at scale, with consistent performance and low failure rates, remains difficult. Huawei's patent introduces some new ideas, but the real test will be whether they can move from lab experiments to full-scale manufacturing. That means building batteries that perform well not just under perfect conditions, but in everyday use across different temperatures and driving habits. Breaking down the specs. Huawei's patent highlights three main performance figures: an energy density between 400 and 500 watt-hours per kilogram, a driving range of up to 3,000 kilometers under the CLTC standard, and a full recharge time of just 5 minutes. To understand how significant that is, consider the current top-performing EVs. The Tesla Model S Plaid uses lithium-ion cells with an energy density of around 260 watt-hours per kilogram and delivers an EPA-rated range of about 630 kilometers. The Lucid Air Dream Edition is in the same range, with slightly higher efficiency. Even if Huawei's design only reaches the lower end of its claim, that's still about a 50% increase in energy density. That kind of improvement could either double the range of an electric vehicle or allow for smaller, lighter battery packs that free up interior space or reduce overall weight. It's also important to understand how range is calculated. Testing standards like China's CLTC often produce higher range numbers than the EPA or WLTP standards used in other regions. Consequently, Huawei's 3,000-kilometer figure may not hold up under stricter testing. Even so, a range of over 2,000 kilometers would still put this battery far ahead of anything currently on the market. The 5-minute charging claim is even more aggressive. Today's fastest public chargers can deliver up to 350 kilowatts, but even then, most EVs need at least 15 to 20 minutes to reach 80% charge. Charging a battery from 0 to full in 5 minutes would require the cells to handle extremely high current, likely in the range of 6C to 10C charge rates. That puts a lot of stress on the battery, both in terms of heat and internal pressure. To make that possible, you'd need a thermal management system capable of pulling heat away quickly and evenly. You'd also need a battery management system that constantly monitors and adjusts voltage, temperature, and pressure across thousands of cells in real time. Cost is another major factor. Solid-state batteries, especially those using sulfide electrolytes, are expensive to manufacture. The dry room environments and specialized materials push cell-level costs to somewhere between $140 and $200 per kilowatt-hour. That's higher than the $100 to $120 per kilowatt-hour typical of current lithium-ion production. Luxury vehicles might absorb those costs at first, but broader adoption depends on improving production yields and scaling manufacturing. If companies can consistently produce high-quality solid-state cells with minimal waste, costs could come down and reach parity with today's batteries within the next decade. Costs might be high now, but whispers suggest Huawei is already testing something far more advanced. Are these just rumors? Or has Huawei secretly built working prototypes of this battery? Rumors and speculations. While the patent gives a technical outline of Huawei's battery concept, there have also been reports and unconfirmed claims coming from people said to be close to the company. Some sources suggest that Huawei has already built small prototype modules using this battery technology. These test units reportedly contain hundreds of solid-state cells connected together and have been used in lab environments to test charging speed and safety. The same sources say these modules handled rapid charging without overheating or failing, but there's no official data to back that up. There's also talk that these prototypes haven't been installed in any production vehicles yet, but testing may have started on private tracks in Guangdong. Some reports claim that Huawei engineers are working with local EV startups and using modified sedans to run quiet, off-the-record tests. Other claims point to extreme condition testing in different parts of China. One group says packs have been tested in cold weather near the Heilongjiang region, where temperatures can drop below -20 degrees Celsius. Another report mentions heat testing in the Taklamakan Desert, where daytime temperatures can go above 60 degrees. The idea is to test the battery's ability to hold a charge and recharge quickly under both extremes, but again, there's no public data confirming these results. There's also some speculation about the anode. Some believe Huawei is using a silicon-graphite blend instead of pure lithium metal. This could be a practical choice, offering a balance between energy density and cycle life. Silicon graphite is easier to manufacture and generally more stable, even if it doesn't offer quite the same performance as pure lithium metal. A few unconfirmed reports also mention that Huawei has brought in engineers who previously worked at Tesla and that they're using advanced software tools to manage battery safety in real time. This kind of predictive system could help prevent overheating or short circuits before they happen. At this stage, none of these details has been confirmed by Huawei or backed up by official testing agencies. Still, these kinds of early reports tend to influence how the industry reacts, especially in a competitive field like battery development. Even if some claims turn out to be inaccurate, they still shape expectations and drive interest in how and when this battery might reach the market. Real-world production challenges. Turning a promising patent into a product that people can buy is never easy. For Huawei's solid-state battery, there are several big hurdles to overcome. First, the manufacturing process itself is complicated. Sulfide electrolytes require extremely dry and oxygen-free environments to avoid damage. That means factories need special clean rooms where moisture is kept below 1 part per million. Setting up and maintaining these conditions is expensive and tricky. Even tiny amounts of dust or water can ruin a whole batch of cells. Many startups working on similar batteries have struggled with this. A brief failure in humidity control can shut down production for days or weeks while equipment is cleaned and requalified. Even a company as large as Huawei faces a steep challenge, scaling up to gigawatt-hour production levels while keeping quality consistent. Next is the supply of raw materials. Producing these batteries at scale demands high-purity sulfide powders and carefully controlled nitrogen doping. This requires reliable mining and chemical processing partners. Early manufacturing runs may have low yields, meaning more raw material is needed to make each good cell, which pushes up costs. Huawei will also need to set up on-site labs to test every batch of material. Recycling scrap back into the process adds another layer of complexity, with its own purification steps. On top of all that, safety regulations for automotive batteries are very strict. Authorities in the US, Europe, and elsewhere require thorough testing for thermal runaway, mechanical shocks, vibration, and long-term durability. A new solid-state chemistry has to clear all these hurdles before it can be approved for use in vehicles. Automakers and battery makers will also have to solve new challenges in battery pack design. Ultra-fast charging produces a lot of heat, which must be managed carefully to prevent damage or safety risks. This might mean new cooling systems like liquid immersion baths or phase change materials to quickly absorb and spread heat. These solutions add complexity and cost, but are essential for reliable operation. In short, moving from a lab prototype to a mass-produced battery involves much more than chemistry. It takes advanced manufacturing, strict quality control, supply chain management, regulatory approval, and thermal management, all working together. This will likely take years, even for a company with Huawei's resources. Cracking the science is just the beginning, but if Huawei actually pulls it off, who stands to lose the most ground? Could Tesla's EV dominance finally be under serious threat? Impact on Tesla and the broader EV landscape. Tesla currently leads the EV market with its own battery technology, in-house software, and a large supercharger network that has over 45,000 charging points worldwide. The Tesla Model S Plaid can charge at rates between 250 and 350 kilowatt, making long road trips easier with shorter stops. If Huawei's 5-minute full charge battery becomes real, Tesla will face more pressure to speed up its own solid-state battery research. They might also need to develop faster charging stations or explore licensing deals to keep their edge. Other companies are also preparing for faster charging. BYD has introduced public chargers with 1,000 kilowatt power, and Volkswagen and Stellantis are testing 600 kilowatt chargers. Charging networks like Ionity, ChargePoint, and EVgo are upgrading corridors in Europe and North America to support these higher power levels. If Huawei's battery technology works well, we could see more partnerships between battery developers and automakers. This could lead to joint ventures, licensing deals, or mergers to share technology and patents. But it could also lead to legal battles and political issues, especially since many countries want to reduce their dependence on China for battery supplies. Chinese EV companies like NIO and XPeng could benefit if they get early access to Huawei's batteries. This could help them offer better models at higher prices. Meanwhile, established companies like Toyota and Samsung SDI, which have been working on solid-state batteries for a while, might need to adjust their strategies to stay competitive. Government incentives, like the US Inflation Reduction Act and European battery rules, will also shape the market. These policies encourage domestic production of advanced batteries and could affect which companies succeed. For consumers, this means more options and faster improvements in charging. Instead of just looking at horsepower or range, people will start paying more attention to how fast a battery charges and how convenient that is for everyday use. As charging gets closer to the speed of filling up a gas tank, the EV market will enter a new phase where battery chemistry and charging infrastructure become the key factors. Consumer takeaways and practical outlook. For most people looking to buy an electric car in the next year or so, don't expect the 5-minute, 3,000-kilometer battery just yet. That kind of tech is still a few product cycles away. What you can expect are gradual improvements. More cars will use 800-volt systems that help cut charging times by 20 to 30%. There may also be batteries with hybrid electrolytes that offer better energy density before fully solid-state batteries arrive. Charging infrastructure will need major upgrades. To support charging at multi-megawatt levels, utility companies will have to improve grid connections and substations. Fast charging stations will need to be built at rest stops, urban centers, and highway exits, similar to gas stations today. Without these upgrades, even the best batteries can't change how quickly you can charge. Fleet operators and ride-hailing services could benefit the most at first. They have short driving cycles and central depots where they can install high-power chargers. Taxis or rideshare cars with ultra-fast solid-state batteries could stay on the road almost all day, reducing downtime and increasing earnings. These early uses could help pay for infrastructure before prices come down for private owners. Overall, the road to mass adoption will be a mix of new technology, business deals, and government support. Breakthrough batteries like Huawei's will need to work well with scalable manufacturing, steady supply chains, and widespread charging stations. Only then will fast charging like this become common. From taxis to ride shares, early adopters could transform city streets first. But what about the bigger picture? Could Huawei's breakthrough truly reshape the EV future in just a few short years? Final thoughts and looking ahead, Huawei's 5-minute 3,000-kilometer battery patent is a big claim that has caught a lot of attention from markets and engineers. It shows how much the electric vehicle industry wants better batteries that charge faster and last longer. But history tells us that many lab breakthroughs face big challenges when moving to real products. Scaling up, costs, and safety are always major hurdles. In the next few years, we might see hybrid battery designs that combine some solid-state parts with traditional liquid electrolytes. These could help close the gap between today's tech and fully solid-state batteries. By the end of 2025, we could see early pilot battery packs in test vehicles, with commercial launches possibly around 2026 or 2027. It will take thousands of hours of testing, lots of money, and many engineering adjustments to turn Huawei's idea into a real battery for cars. One thing is clear: the race to improve solid-state batteries is speeding up. Whether it's Huawei, Toyota, or startups, the push to create better energy storage is growing. For drivers, investors, and engineers, this means exciting developments are coming. Each small breakthrough brings us closer to a day when a 5-minute charge really gives you enough power to drive 1,000 kilometers. Huawei's patent has sparked fresh energy in the solid-state battery field, but scaling up, cost control, and safety will be the key challenges to watch. Now that we've looked at Huawei's battery patent, it's clear this idea has shaken up the EV world. The thought of charging a car in 5 minutes and driving 1,000 kilometers isn't just a dream anymore. Whether this technology makes it from the lab to the road or stays just a concept, it has made every car maker and battery engineer rethink what's possible. Thanks for joining me on this deep dive into the future of electric vehicles. If you're curious or have your own thoughts, feel free to share them below.